Welcome back to the course on architectural design of ICs. So, here we are seeing different adder architecture. So, we have started with that means basic addition operation, which are this full adder and half adder. Okay. So, after that we will just continue with this. So, this is the addition of binary numbers. Here you see, if I am having this AI, BI, C in, and this is a full adder circuit, that means which will produce this C out and sum output. Okay. So, that we have already discussed how it works, what is the that means working principle of this particular full adder set. So, whenever this working principle of full adder cell we have seen, so at that time from that particular truth table, that means or this operation table of this full adder cell. So, we have come out to this logical expression for sum and this logical expression for carry out. Okay. So, sum for sum, that is nothing but AX or BX or CI. That means, if I just simplify this logical expression, so at that time I will get nothing but AX or BX or CI, AIX or BIX or CI, and the CI plus 1, or that is the C out. So, that is nothing but this AIBI plus AICI plus BICI. Okay. So, that means AB plus BC plus CA, nothing but that I will get. So, after that, that means I need that means there this ripple carry adder, that architecture comes. So, why I need this ripple carry adder? Ripple carry adder I need whenever we are considering n bit numbers. Okay. So, n bit numbers means whenever I am having, that means here we are doing only single bit addition operation, right. So, we are having multiple bit operation, as you might be knowing that that means present days computer that has become 64 bit. Okay. Some of the cryptographic core that is 128 bit long. Okay. So, that means the addition operation, and obviously for this cryptographic algorithm or for any algorithm which is implemented on this particular computer architecture. So, at that time I need to support this addition operation of 64 bit or 128 bit. So, that means I need to design one addition or adder operator or adder circuit which can work with the 64 bit as the input or as the word length of the inputs. So, whenever we are considering this 64 bit addition operation, then at the time how we can design them, that we will see. So, this ripple carry adder says that the carry is basically rippling. So, why carry is rippling? Okay. So, if I consider, suppose this is the 4 bit, that means ripple carry adder, or I need to design one 4 bit adder. So, 4 bit adder means I am having this as A and B of each of 4 bit. So, each of 4 bit means for, if I consider A of 4 bit and B of again 4 bit, right. So, 4 bit means that is A3, A2, A1 and A0, now B3, B2, B1 and B0. I have to add these two numbers. Okay. So, now whenever if I just add these two particular bit, so if I am considering only these two LSB bit position, so at that time what will happen? This is nothing but a full adder, right. So, nothing but a full adder cell means there is no other input which are affecting basically this particular logic. So, that is why there is A0 and B0. So, what I said that initially, that is this is binary weighted values. So, that means this is 2 to the power, this is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2 and this is 2 to the power 3. So, whenever I will add these two particular bit position, at that time the carry out which is generated for these two addition of these two bit, that will come to this 2 to the power 1. Okay. So, that means now for these two particular case, or whenever I consider this but bit position. So, at the time it is not that only A1 and B1 they are basically evolved or involved for specifying this the sum value at this particular point. Why? Because this carry which is generated from this the previous level, that will also affect the corresponding sum and carry values. So, that is why at that time it will not be one half addition or half adder operation. So, at that time what it will be? It will be like A3, A2, A1, A0, and if I just add B3, B2, B1 and B0. So, at that time for these two, this is half addition operation, and for this there will be one, if I consider this is sum 0 and this is the C0, okay. Or if I just say this as a C1, let us consider named as C1. So, that means this is a carry which is generated from the this A0 and B0. So, now I can add these particular things, and again I will get what 1 and 1, that means 1 and 1 means this carry and sum. So, that means from this particular block this will be S1 and this will produce the carry as C2. Then again for this do the same, that means it will produce the corresponding S2 and this will produce the corresponding C3. Then for here S4 and this is the final carry out. Okay. So, that means if I just want to add this A and B are of 4 bit. So, at that time I will get the output sum as 4 at the sum and 1 for the carry output bit. Okay. So, here the point is that now if I just draw this particular circuit for this addition operation, then what I need, if I just draw the block diagram of this. So, at that time how it will look like? This is A0 and B0, this is one half adder, then the carry C1 is basically comes over here, then A1, B1, this is S0, this is S1, then this will produce the C2 where this will added with A2 and B2, then this will produce S2 and this C3 which is nothing but it will add with A3B3, it will produce S3 and it will produce a C4. These are the 4 adder cells. Okay. So, now if I just, that means if I just what I said, if this is my total this 4 bit adder circuit. So, at that time what will be the operating frequency of this particular circuit? So, to find out the operating frequency, what I need that? I need to calculate the corresponding critical path. So, here what is the critical path? The critical path basically where from it is starting? It is starting from any of these two LSB bit position, then that basically logic is transferring from this to this, this to this, this to this, and up to here this is basically this carry is basically traversing. So, that is the longest path in this particular circuit. So, the longest path means that is the That longest path means which is passes through several maximum number of gates in the corresponding circuit. So, that is the critical path. So, now this critical path, if I consider this delay for this is for full adder is Td and for this is Th. So, then the critical path is 3 of Td plus T of H. Okay. So, if I increase this number as 32 or 16 or 64, so at that time this will also increase. So, if I just do it, if I just for 16, if I just need make it, so at that time what it will be for 15 Td plus Th. Okay. So, one full adder cell what it consists? It consists of 2 XOR gate, 2 input and 1, 2, 3 AND gate and 2 OR gate for implementing this, for implementing the carry logic. Okay. So, now that means for whenever we are doing this, so at that time the max of XOR gate or this AND plus OR gate delay, that will be the critical path for, or that will be the delay for one particular full adder cell. So, if that is, if I consider that as in 2 nanosecond and for half adder, the delay if I consider as 1 nanosecond. So, at that time this will be of 31 nanosecond. So, that means the operating frequency of this particular circuit, that is 1 by 31 nanosecond, that is near about I think 330 megahertz. Or not 330, I think 30. Let us consider 30 or 32 or something like this, 32 or 30 megahertz. Okay. So, this if I increase this number on the more, that means at that time the rippling time or the carry rippling time from LSB to the MSB, that becomes more. So, that is a disadvantage of this particular circuit. That means, whenever we are considering for more number of bits, so at that time you can get a larger number of delay. Okay. So, for that reason, if you just see here, that means these are the that means 4 full adder cell and the worst case delay linear with the number of bits, what I said. That means, if I increase the number of bits instead of 4 bit, if I consider 8 bit, so the corresponding delay, worst case delay, that will be increased linearly. If I increase the number of bits, the delay will also increase. So, that we have already seen. And then after seeing this particular problem or seeing this challenge, what will be my target? My target will be how I can make this addition operation as fast as possible, and what is this carry path is that means critical path. So, how can I break this particular critical path so that I can improve the operating frequency of this particular circuit. Okay. So, that is our intention. Okay. So, actually for that, what people have that means done the inversion property. Why I need inversion property? So, if you see that for implementing this A XOR B XOR C, okay. So, for implementation of this, I need the inverter circuit at the output of that. Okay. So, it is not that it is, that means it is not, it will not give you the corresponding that expression for AB plus BC plus CA. So, you can get it, and then if you just see, that means if you just see that transistor, that means NAND gate level implementation. So, at that time you have to, that means put one inverter at the output, as it is not coming as, here I need, that is, or the operation is coming as NAND operation. So, I need AND operation. So, I need one inverter at the output, final output, for making the NAND to the AND. Okay. So, for that reason, to reduce the number of transistors, so what people have done, from the beginning they have put that instead of A, B and C, they have taken the now, that means these corresponding values invertedly. So, that means the complement of A, B and C that are being used for in this particular full adder cell. Okay. So, and here you see that this is basically the that means addition operation or implementation or using these transistors, where I am doing initially we have just inverted, and then we have just put this into the this corresponding full adder cell, or for this sum and that means carry out that circuit. Okay. But here you see, only for this this inversion is done on the corresponding this even position. Okay. For odd position, it is not done anything. Okay. So, by doing this kind of architecture, you can reduce the delay by inverting the corresponding that means this the even stage. I can reduce the critical path, or I can reduce the, or that means this critical path that can be reduced, though it follows the same, which is nothing but the carry ripple adder. Okay. So, and this is the, that means this transistor level implementation, okay, of this, and here you see the critical path is this basically, which is following or which is passes through each of this bit position or each of this full adder or half adder cell. Okay. So, this is the, that means this this ripple carry adder implementation using the standard cell library. So, now again come back to the corresponding operation table of the truth table, the full adder. So, here you see, whenever this for this 0 1 and 1 0 of input A and B, whenever this carry bit is 0, okay. So, at that time this carry output bit is 0, only the sum is 1. But whenever this A and B, they both of them are 1 1 and carry is 0. So, at that time the carry out is 1. Okay. And the same thing for this last one, if you see for 1 1, if the carry is input is 1. So, at that time sum is 1, but the carry is already 1. So, that means now for this 1 and for 1 1 of A and B, it does not matter whether the carry input bit is 0 or 1, the carry output bit will be always set to 1. For carry in bit is 0 or 1, only it is affecting what? This sum value, whether that is 0 or 1. Okay. So, here that means this I can say the carry is basically propagating, sorry. So, the carry is being generated. Okay. So, then how this carry is being propagated? If you just go back to the previous slide, whenever this 0 1 and 1 0, whether that carry bit input bit is 0. So, at that time this carry output bit is 0. Whenever this 0 1 and 1 0, if carry input bit is 1, so at that time carry output bit is carry output bit is 1. So, that means here the carry is being basically for this particular case the carry is being propagated. So, propagated means based on this, if this particular combination happens. So, at that time based on this carry input bit, the carry output bit will be selected, whether that is 0 or that is 1. Okay. So, then from this, if I just write this as carry propagated, if you just go back for 1 1, sorry, for 1 1 and for 1 1 over here, this is that. So, for carry generation, the logic is that is A and B, AI into BI. For propagation, what is that? For 0 1 and 1 0, what is there? That is that means the logic is that A XOR B, and that is ANDed with 0. That means for both the cases the sum is 1. So, now if sum that carry is 0, then carry in is 0. So, that is 0. If carry in is 1, so at that time carry out is becoming 1. So, that means that logic for propagation logic I need A, that means for sum, that is which is 1, sorry, for carry for carry propagation the logic is that AI XOR with BI. Okay. So, now for carry output bit, I said that the one logic for carry output is AB plus BC plus CA. The another logic for this carry output bit is this another logic for this is that is AB plus A XOR B into C or C in. Okay. So, if I just come to this particular logic, so at that time if I consider this carry for carry generation, I am considering this AI and BI. For carry propagation, Pi equals to AI XOR BI. So, now I can write this C out as the function of Gi plus Pi into Ci, where Ci is the input. So, now this is the that means corresponding logic for or the corresponding gate level implementation of this particular logic or this particular function. Okay. So, here you see that this particular is for this propagation, and for generation what I need? The corresponding AND gate. Okay. So, after that this is the that means this Pi into Ci is done, and then that is OR with this Gi, and this is the final Pi plus Ci for doing the sum, and this is for the C out. Okay. So, what is the problem in ripple carry adder is that I have to wait. If I just go back to the slide, if I just go back to the slide. So, at that time if you see, here at this particular point, okay, at this particular point, unless and until this C 0 is basically computed, I cannot start the operation of this A 1 B 1. Then again this, unless and until this carry is being generated here, I cannot start the operation of this particular full adder cell. Again for this, again I cannot start this. So, that means that is why I have to wait for this carry has to be available at this particular time. Okay. So, that is basically the bottleneck in ripple carry adder, as the carry is rippling, or the carry is basically passes through this all these particular phases or stages. So, unless and until this computation is over, it cannot start the next computation. Okay. So, that means it is a serial operation, but whenever we are doing this, doing this, that means we are generating, propagating the carry, that means first, and then generating the carry 2, and then I can, that means in each of the stages I am basically producing this carry generation and carry propagation parallelly. Okay. So, how we can, that means this is for one, that means single bit operation. Okay. So, then again for here, actually what I am doing, I am just propagating, and using this I am just generating. Okay. So, instead of that, if I just use one mux over here for calculating the C out. Why C out is calculated? So, you see C I plus 1, that is equals to G I plus P C I. So, G I is the carry generated, P I is the carry propagated, right. So, for this particular case, it is producing the sum. At this particular point, if you just see what is the logic for mux, here you see this A I B I, that is the select line, okay. And then this two input is, one of the input is A I, another input is C N. Okay. So, now if you just implement this logic, that means whenever this, if I just go back to this. So, what it says, whenever this is basically 0, that means this is the this A I, sorry, if I consider this A I plus B I, okay. So, if I just, here at this particular point, this is what AI XOR with BI, correct, for this propagation. But if you just see, depending on the carry input bit, I am getting the carry output bit. How? What is the logic? If my carry input bit is, that means if this is the, that means this is fixed, right. For these two particular case, wherever this carry input bit is 0 0, sorry 0 0, so at that time carry output bit is 0 0, whenever this bit is 1 1, so at that time carry output bit is 1 1. Okay. So, that means now if I just consider this, that means this is the C in, which is at 1 and this is at 0. So, that means for XOR of this AI and BI, for 0 1 case, for 0 1 case, what is happening? For 0 1 case or 1 0 case, in both the case, this particular circuit is giving me 1. So, that means as C in is the as same as the C out. So, at that time I can get the results at the output of C out. What will happen for this 1 and 1? For 1 and 1 and for 0 and 0, both are 0, right. So, at that time if I see that for 0 0 this case and for 0 0 this case, the Ci is changing from 0 1, but here does it basically happening as 0 1? No. For 0 and 0, for 1 and 1, this AI XOR BI, that will be 0 in both the case. So, at that time I need to select this 0 line, and at that time what is the output of Ci? That is 0 at this particular point and 1 here for this, and same for 0 0, for 1 1, for 1. Okay. So, that means any of the input bit, whether that is AI or BI, that will be connected to, because at that time what is happening? AI equals to BI, okay, for 0 0 and 1 1 case. So, any of the input bit that will be connected at this 0th position, and that will be the C out at that particular point. Okay. So, that using if I just using these marks, now I can implement the same function. Okay. Oh, so where this is the select line input and this is the AI and BI. So, this is used for high speed addition operation. So, high speed addition operation means I can improve, or I can, that means from the beginning what will be the values of carry input bit, sorry, the carry output, if I can predict and I can select the corresponding value. So, by that I can reduce the computation time of carry whenever we are considering a long chain of addition operation. Okay. So, thank you for today's class. Again we will discuss it on the new classes. Thank you.